Clustered, regularly, interspaced, short, palindromic repeats, otherwise known as CRISPR. It's a word many people know is associated with genetic engineering. But what most of us don't know is what exactly is genetic engineering. The science of adjusting the genetic makeup of plants has been in process for thousands of years. From the time humans transitioned from hunter-gatherers to farmers, we've been tinkering with food. This plant has that characteristics, and if I wet it to this one, will it grow better in this environment? Will it taste better? Will it be drought resistant? Will it be disease tolerant? And so on. By the middle of the last century, scientists were rapidly moving toward sequencing the genomes of everything, including people. Genetics now play a vitally important role in innovations in medicine, trees, food, and so on. And somewhere along the way, genetics and food got a bad rap. So much so that many people are openly campaigning against bioengineering of plants. I wanted to ask someone who actually does this type of work what they do, why they do it, and can we trust them and the foods they produce. I invited Larry Gilbertson of Bayer Crop Sciences to join me for a conversation that matters Food for Thought episode about innovations in plant biotechnology. Larry Gilbertson, welcome to this episode of Conversations That Matter, Food for Thought. You know, the topic today is really about genetic engineering or bioengineering of food, which gets labeled as GMOs and a wide variety of other aspects in working with the plant to try and enhance their ability to be more productive. Yet it kind of gets a little bit of a bad name. I want to start with the idea that, and I'm trying to get a sense that this is true, that are not all the foods that we eat in one way or another, that they have been biologically engineered, whether it's through hybridization or crossbreeding or mutagenesis and so on. Can we actually say with some accuracy all food has had some sort of genetic modification?
Yes, Stu, I think that's an accurate thing to say. So one way you can think about it is go to the produce section of any store, look at your broccoli, look at your apples, look at your carrots, and then go out and find that somewhere growing in the wild. You'll find progenitors of them growing in the wild, but you won't find anything that looks like what you find in the produce section growing in the wild. And so how did we go from what grew in the wild to what you find in the produce section now? It's humans have actually been changing the plants and the food that comes from the plants over the years, long before they knew that there were genes and genetics and DNA. They were actually changing that unknowingly to them by always selecting the best looking carrot or the best apple and then improving those over time by planting those back. Mm-hmm. And so for thousands of years, humans have been changing the DNA. So in a sense, yes, the food has been genetically modified because when they've been doing that, they have been changing the genes and changing the DNA within those. So that's true. Now, in modern days, when we talk about genetic modification, we usually talk about something with more modern technology. But I think you are absolutely right. And it's good to keep in mind, especially when we start to talk about modern methods like breeding, gene editing, and even GMOs.
As you're talking, I'm thinking, okay, I remember reading Guns, Germs, and Steel by Jared Diamond, and he talks about how the introduction of agriculture into the human experience, we've gone from being hunter-gatherers to now all of a sudden realizing, hang on a second, if I stay put and I actually tend to this patch of land, I can produce more food for a longer period of time. And while I'm producing the food, you can do something else. And so agriculture has been fundamentally important for our development as human beings. And just by the fact that we're putting these plants in close proximity with one another, we start to change the genetic makeup. Do I have that right?
Yeah. So putting them close proximity to each other may be changing the genetic makeup, but really the bigger driving force in changing the genetic makeup is always looking for plants that have some trait, something about them that's more desirable for the humans. So it could be that it tastes better. It could be that it's easier to grind it and turn it into flour. It could be that it just produces more, because fundamentally production is important to drive populations and civilization and so on. So again, over time, as humans had been always selecting for whatever are the desirable traits, taste, storability, just production and so on, they've been taking those natural variations that already existed and starting to shape them and essentially modify them in certain ways.
The work of Norman Borlaug and the Green Revolution, how revolutionary was that going back to the 1940s and 1950s? Because he actually was going out and looking and crossbreeding thousands, hundreds of thousands of different strands of wheat. And that is painstaking work. How do you wind up getting a productive outcome? I interviewed Charles Mann, who wrote the book The Wizard and the Prophet, and he said, here's Borlaug, who's going through all these things, and he's going, okay, well now I got a shorter stock, so I'm not going to get when the wheat will collapse. Lodging, yes. So I get a shorter stock and I get a bigger spikelet, but I don't have the right taste. But he didn't have the benefit of science that we do today. That was incredibly painstaking work, but still he starts to wind up with a result where we see a tremendous burst in productivity and abundance of food, where there hadn't been that abundance before.
Yeah, that's a great story. I'm a big fan of Norman Borlaug and the Charles Mann book about him. So Norman Borlaug came along after we knew what DNA is, and we knew about genes, and we knew about genetics, and plant breeding in the modern sense was already starting to happen. One thing that I admire the most about Borlaug was really just his hard work and his passion, because as you said, he made a lot of his progress through individual, meticulous, tedious crosses of plants, for example, wheat, taking the pollen off of a wheat plant and carefully using it to cross onto another wheat plant manually, one plant at a time. And so it's just pure hard work combined with his passion. But at the same time, we also already knew at that point that genetics was something that we could actually breed for. And so what he was trying to do is try to solve some problems with wheat. First off, a disease that infects wheat and it can actually wipe out a wheat crop for a farmer. He also was trying to find ways to produce more on a wheat, on the head of a wheat, more seed, bigger seed, and so on. And as he became more and more successful with that, he started to have another problem. And that was that the heads of the wheat became too heavy, and the wheat plants tended to tip over, especially if it was windy. And so now he started turning his eye toward, can he get that same kind of productivity by, but using a shorter plant? And again, genetics came to the rescue, because there are already variants out there, variants in the DNA of wheat plants, that if you bring them together in the right combination, you can get the best of two worlds. You can get the disease resistance that he was originally breeding for, but then also be able to make the plant shorter so that it can stand up taller. So it's amazing what you can do through just pure hard work and understanding of genetics. And as we've advanced in the last 40 or 50 or more years since then, that was back in the 1940s that he was doing that. Now we're using more and more tools, but we're fundamentally doing the same thing. We're essentially looking for variation that exists in these populations of wheat, of canola, of your favorite crop, and bringing them together in new combinations that didn't exist before, and then carefully looking through all those new combinations to find out, did I actually improve something about the plant?
So one of the things that I found really interesting about Mr. Borlaug's story, of course, is that he was originally given the assignment of addressing wheat rust, which he did, and different strains of it. But at the same time, also, there was starvation in India and in Mexico, where they were importers of wheat rather than exporters, and populations were growing. That was a world of about 2 billion people. We're now north of 7.5 billion and growing rapidly. And I have been told that between now and the year 2050, when we get into 9.5, 9.7 billion people, we now need to be able to produce enough food that is the equivalent of the last 10,000 years worth of food. We don't have time to go through the work that Norman Borlaug did to try and find that next advance. And so science now starts to play a role. But for most people, they go, ugh, now I'm starting to become a little bit leery of this. What can we do to help put people's minds at ease about the fact that what we're doing is we're trying to enhance the resilience, the productivity, the abundance of foods that we're all going to need?
Yeah, I am a scientist, and what you just got done describing, the population of the Earth is going to be close to 9 billion, maybe 10 billion by the year 2050. We're not generating any new land to grow on. If anything, land is shrinking because the population is growing. And this is what really drives me, because I believe that science can play a very important role in solving some of these big challenges. And so we need to, as you said, we need to make even more advances in the next 30 or 40 years than were made since Borlaug's time. And so we need all of the tools that we can bring to bear on this. It's not all about breeding. It's definitely not all about GMOs. It's not even all about gene editing, which is one of the new exciting technologies. It's going to be some combination of those and bringing the right solutions and the right tools at the right time for the right problem, be it diseases of plants. A lot of people don't realize plants get diseases just like humans, and they need to be able to fight off those diseases. Nutrition, productivity, and we have to figure out, if that wasn't challenging enough, we have to figure out how we're going to do this in a sustainable way. We can't do this by we can't continue to do this by continually adding more and more and more inputs. We have to figure out a way to be able to manage that better and do this in a sustainable way, even in the face of other challenges like climate change. So as a scientist, I see this as a great opportunity. I'm confident that the science can help provide some of the solutions for this, and that's really what drives me. Now, how do we get people comfortable with this? I think one way we do it is by talking about it just like this in a public forum. I think one thing that we scientists have not done very well in the past was engaging with the public. We tend to stay in our towers and stay in our labs and so on. So it's important that scientists get out there more and engage with the public and actually hear what they have to say and hear what their concerns are. Talking about science, explaining it a little bit more, although that's not always going to do the trick, but just being part of the conversation and engaging with the public, because I do believe that the science that we can bring to bear on this is really going to help solve some of these solutions. We just need to have it become a public conversation and not just a conversation behind university doors or company doors.
You touched on a couple of interesting points there. It's not just about expanding the abundance of food, but it's how does that food or that plant reside within the pod that it's growing in? How's it drawing nutrients out of the soil? How is it its own resistance to diseases or insects that want to eat it? How does the plant play a role in helping us deal with climate and environment? Are we able to get that specific when it comes to looking at the genetic structure of a plant and say, okay, I can see that this seed is going to be growing in an area that is more prone to drought. So can we make it drought resistant? And versus the one that's going to be in a wetter environment, do we change that seed so that in that environment, it will be able to survive?
Yes, I think that's absolutely true. I think we can breed plants, we can modify plants, and move them in directions such as make them more resistant to drought. So, for example, as climate change comes along and continues, we know that this is going to lead to more extreme weather patterns, not always just hotter temperatures, but in some cases drier, in some cases actually wetter. And so plant breeders and plant scientists are really beginning to understand what the genes are, and especially what the variation in the genes are that will help us to shift the plant to become more drought resistant. One of the greatest things that has happened in the last 10 or 20 years in plant breeding isn't so much about the actual physical breeding part out in the field and then observing out in the field, but understanding all the DNA, all of the genes, and the variation in them. There's about 2.4 billion letters in the genetic alphabet in corn. There's about a little over 1 billion letters in the alphabet of canola. But if you take plants from one part of the country and plants from the other part of the country or from other parts of the world and compare their DNA, those 2.4 billion or that 1 billion, you're going to find thousands and thousands of differences in the DNA between them. And amongst all those differences, those thousands of differences, is the key to being able to shift plants, to breed plants to be more resistant to drought, or to be able to take more flooding or rainfall or salinity and so on. So using advances in data science, using computational advances, we've really gotten better at making the connection between those variations and then what we observe in the field. Because we know that there are some plants that are just better at growing in drought. And so what we've been able to do in the last 20 years, especially, is start to understand at the genetic level, at the DNA level, what is accounting for that difference. And then we can breed more smartly, and then we can start to use new tools like gene editing to actually create that desirable variation.
So agriculture is very, very site specific. You know, my farm is here in this county and yours is one that's 100 miles away. We can be in quite dramatically different growing conditions. How do you as a scientist then start to say, okay, here's what you need and here's what I need, and how do we go about making that possible so that you can produce or that we can both produce food? Like, it has to be painstaking work that's very site specific. It almost seems like it's too much to do.
Yeah, it's true. Now, to a lot of people, if you drive across Ontario and see the corn there, and then drive into Minnesota and down to Iowa and see the corn there, it looks the same to most people. But in fact, it's very different. The corn that's bred to grow in Iowa is different than the corn that's bred to grow in Ontario. So there's lots and lots of different varieties out there. We understand that there's the interaction between the genes and the traits, what we call the phenotype, what the plant looks like and how it behaves, also depends on the environment. And a fundamental equation that we talk about all the time in plant science is G crossed by E equals P. So G is genetics, E equals environment, and P is the phenotype, or what the plant looks like and how it is. So it's actually the combination of the genetics and the environment that will say if a plant is drought resistant, or if a plant is resistant to a disease, or if it has a lot of kernels on its ear if it's corn. And so it's not just about the genetics, it's about the genetics interacting with the environment. So that's another layer of data that we need to take into consideration as we're trying to improve crops.
Well, even in Iowa, for instance, the corn that is going to be for human consumption is going to be different than the corn that's grown for as feed for ruminants and other farm animals. So it becomes very specific. What does it take then for you as a scientist to say, okay, I'm going to do this for this specific area? What's the process? How long does it take? What's the regulatory environment in which you work in? What's it cost to make a change in the genetic structure of a plant and then actually be able to take it to market?
Yeah, so first of all, it takes a broad testing network. So it would not be possible to do all of our testing right here in Missouri, for example, but trying to improve plants that will be grown in Ontario or in Manitoba. And so first, you need a broad testing network so that your scientists, your breeders, can actually make improvements and observe them and improve them in those areas. This does take a long time. Just think about how long it takes, first of all, just to plant a seed and have it grow up and be able to cross that plant to another. Depending on the plant, this could take months. Think about seasons. You can't do this in the dead of winter. And so now you'll have to either wait until the next season or go someplace else in the southern hemisphere, for example. Takes a long time. Then there's the testing. And so as these varieties are being developed, whether it's through breeding or biotechnology, gene editing, there's testing, and the testing also has to be done in those areas as well. And so it does take time. It takes years. A typical biotech, GMO type of improvement takes at least 12 years from the time when you first have the idea for how to do it to when you can do all of the testing, do all of the testing required for regulatory, do all of the pre-commercial launch will take at least 12 years and well over $100 million. Breeding can be a little bit faster, but not that much faster. And gene editing is a way that could potentially shave off some time off of this, but you're never going to get around the need to test and test in multiple seasons and multiple locations, and then also do some of the work that you have to do to answer regulatory questions about this. So, and the need is now, of course. We need to start doing this now. And so that's why we hope that we can find ways to do this faster, either the genetic engineering itself or the testing or providing the answers to the regulatory questions. So, for me, I feel a sense of urgency. And I'm at the point in my career now where some of the things that I'm starting now, I'll probably be sitting on my porch in the rocking chair by the time they're actually grown in places like Iowa and Ontario. But for me, it's a sense of urgency. And so we're always looking for ways to find ways to do this faster. However, there are certain things you just cannot do faster. Growing the plant, testing, multiple seasons, multiple locations.
Okay. So that helps to sort of put to rest some concern that, you just go into the lab, you make some little gene switch and you plant it and away we go. No, there's a tremendous amount of rigorous testing that goes into that. But then we start to run into a regulatory environment that is not so keen these days on saying, okay, we're going to give you the authority to actually grow that. How do we classify where that regulatory mindset is? And like the seeds themselves, it's different in every jurisdiction.
Yeah, that's one of the most complicated things about this is that the regulatory landscape, as they say, how different countries look at these crops from a regulatory perspective changes from country to country. And so I think the most important thing is that we would like the regulatory policies and the regulatory actions to be based in science. I think for the most part, they are. And so it's important that they are based in science. I think it's also important that they look at the product, because that's actually what's going to be grown in the field and then end up in grocery stores, for example. And it's also important that we find a way for the regulatory agencies to keep up with advances in science, because as you know, science can advance really quickly. A great example of that is gene editing, what I work on now. It's only been about 6 years since this technology was even imaginable to be using it in the way that we're doing now. And so, but here it is now. It has a lot of potential, and a lot of entities, universities, small companies, big companies, are all developing future crops that are based on gene editing. And yet the science behind it has only been around for 6 years. We know a lot about it, but the challenge is for regulatory agencies to be able to keep up with that. And I think that's another reason why scientists, whether at companies like me or at universities, need to talk more about this and get out of their labs and get out of their buildings and engage with the public and, of course, with regulatory agencies as well.
Well, I agree with you. That dialogue is vitally important. For the average person who would be like me, I start to read this material, and after about the third sentence, I start to lose my ability to make sense of it. And so we need people like you who can actually describe what is happening in a manner in which we can comprehend. And I think that if we're able to remove that shroud of mystery, then people will start to understand that there's no malicious intent here. As a matter of fact, it's all designed to ensure that everybody has the food that they need to ultimately realize their own potential as human beings, which, as Aristotle pointed out to us, is our responsibility. And when that happens, all of society benefits.
Yeah, it's definitely a sense of urgency for us. The intent here is we really are trying to help solve some of these huge global challenges, especially with food, especially with agriculture. And it is complicated. It's the science is complicated, but there are very simple ways to think about this. I think, of all of the DNA that's in you, that's in me, that's in a tomato, that's in a corn plant, it's basically like a big cookbook. It's the recipes. It's the recipes for everything, and there's thousands of individual recipes in there, and they all come together to form a feast, basically, or in our case, make us, or make a fruit fly, or make a corn plant. And so it's really just recipes. And just like any cookbook, as you modify those recipes and they get passed down from your great-grandmother to your grandmother and so on, little changes happen. And it may be that somebody's just changing the temperature of the oven by 30 degrees. It may be that somebody's actually just removing a recipe. And this is exactly how it works in nature, that it's basically a recipe book that is changing over time, evolving, and the ones that work the best, the recipes that make the best food or the tastiest food and so on, those tend to stay in. And the ones that aren't working so well, those tend to go out. And so breeders have basically been taking these cookbooks and shuffling recipes around by the dozens or hundreds at a time. And you can do that if you shuffle thousands and tens of thousands of them and then have a way to test them all, put them all in the kitchen and test them. And then with GMOs and biotechnology, what we're doing is basically adding a recipe. This is a great recipe. It's got thousands of recipes. This is a great cookbook, lots of great recipes, but here's another great one. Let's put that one in. And then gene editing is like going into that recipe book and saying, this is a pretty good recipe book, but let's just tweak this one recipe. Let's just tweak this other recipe. And that may sound like an oversimplification, but that's basically what we're talking about here when we're talking about improving crops by changing its DNA.
Yeah. Well, thank you very much for taking the time to give me a glimpse into your world and to have a better understanding of the world of genetic engineering in agriculture.
It's my pleasure.